Most people take their washing machine for granted, except for the occasional outburst of hatred when the thing goes wrong. But in fact, they're wonderful feats of human ingenuity. Although they're now so commonplace, it's taken an enormous amount of time and effort to perfect their design. Only 30 years ago, automatics were rare, expensive luxuries. And 70 years ago, they were only the most primitive hand-operated machines.
All washing depends on squashing water through the fibres of the fabric. Soap helps to dislodge the dirt and carry it away in the lather.
The first step towards mechanisation was the dolly. This was pummeled up and down in the wash tub and avoided the need to get quite so wet and also the need to bend down. From this, in the late 18th century, various hand-operated washing machines were patented. In fact, these hand-operated machines continued to be made till well into the 20th century. This one's called the Eddy, and it actually works quite well. The backwards and forwards action stops the clothes getting tangled, and the paddles bash the clothes just hard enough to wash them, but not so hard that it tears them to bits.
An early, more radical departure from hand washing had been used by sailors for centuries. The combination of agitation and a constant flow of clean water washed them fairly effectively, even without soap. Another way of forcing water through the clothes is to make them tumble over each other in a drum. The earliest record of a machine of this type dates from 1782. This was the forerunner of much larger laundry machines that rotated the drum and heated the water with steam. In many respects, laundry machines have remained unchanged, with the clothes tumbling over each other in a large drum. But although 140 years ago the basic principles of industrial machines had been perfected, domestic machines remained extremely primitive. The arrival of reasonably small electric motors at the beginning of the 20th century made a large number of washing actions possible. These early machines were particularly popular in America, where they were viewed with great pride. This machine was imported from Canada to Britain in the 1920s. The motor sits underneath, connected by a system of belts and gears. It's really rather a splendid contraption.
Inside there's a paddle that goes backwards and forwards, very much the same shape as the old washing dolly. But these machines had very serious disadvantage, that they often leaked quite a bit, and the water used to drip down on the motor and the switch and all the wires. And because water's a conductor, the whole machine could easily become live. I mean, I've just got a little shock off this. Safety was quite an important reason for enclosing the whole machine in a single case like this, with motor and wires and tub all in one. The first machines like these, looking a bit like a modern washing machine, appeared in the mid-1930s.
The water still had to be heated in a separate wash boiler.
How's it coming, Lynn? So there I was at 20,000 feet.
The idea of a fully automatic washing machine came from America. The first ones appeared in the 1920s, but it was another 30 years or so before they started to become practical labour-saving devices.
Brother, get this, Carol. What does the emancipation of American women mean to you?
I know. Women's right to vote. Why, it's the biggest thing that's happened to women since
Adam's apple. Carol, you sweet dumb thing. Pull up your flaps. You're dragging.
Oh, my gosh. That's a terrific angle. Talk about emancipation. Take the family wash, for instance. No more clotheslines. No more dark basements. No more Blue Mondays. Boy, here's real emancipation from old-fashioned chores. Just set a dial and walk away. Well, that's the kind of emancipation any woman can understand.
The first automatics appeared in Britain in the 1950s, imported from America. These machines were extremely expensive, costing as much as a small car, and most households still had no washing machine at all. Then in the early 1960s this machine appeared. It wasn't fully automatic, it had separate wash and spin tubs, but it was, compared to all its competitors, amazingly cheap.
Which twin tub should you buy? Independent tests show Rolls as good value for money. So if you want a twin tub that's good and quick for washing, easy to use, electrically safe, good value for money, and also gives up to a maximum of £35 in part exchange, then you must choose a Rolls. Yes, a Rolls. For full details of the Rolls Concord models and this week's special offers, fill in the Rolls coupon in today's papers now.
The Rolls company, owned by John Bloom, went bankrupt in 1964, but by that time had enormously expanded the market for washing machines.
Well, so much for the history. But how does a modern machine actually work? Well, Rex Garrett and I have made a series of models and demonstrations to explain some of the mysteries of what's inside a modern washing machine. Well, one of the first things you notice when you take the top off is often an enormous lump of concrete.
On this machine, we've taken those large blocks of concrete out so you can see exactly what happens.
The concrete's there to damp out the machine's vibrations. Well, every structure or machine has natural resonant frequencies at which the vibration can become excessive. Occasionally, this can be useful, as I'll show you. This is a thunder machine.
I made it for a theatre company.
The eccentric weight on the motor is a bit like the washing in the drum, which is never completely balanced.
The noise is created entirely by vibration. The weight never actually touches the steel plate. In industrial laundry machines, the effect is much greater, and older machines had to be bolted to the floor with massive foundations. Modern laundry machines don't vibrate nearly so much. They automatically balance the load by pumping different amounts of water into the triangular pockets round the drum. The lights show which pockets are being filled. Of course, domestic machines aren't so sophisticated and have to make do with their lumps of concrete.
And if you chop a modern machine in half, you realise what a vast number of bits and pieces there are. And of course, each one of them could go wrong in all sorts of ways. The real miracle is that most of them work perfectly all the time. The first thing that happens when you turn the machine on is that water gushes in, released by a sort of electric tap called a solenoid valve. Simply pass the current through it and the valve opens. The clever thing about these valves is it's just a small cylinder and a small coil, and it has to resist the full force of mains water pressure. So I have to actually put my finger over the edge quite hard to stop the water coming out. Whoops. It does this by using the pressure of the water itself to stop the water coming out.
This part is the solenoid, a sort of electromagnet. The steel piston in the middle is attracted by the magnetism and pulled in when the current is switched on. The piston rests on the centre of a rubber disc which acts as the seal. In this disc there are two tiny holes. The hole in the side lets water into the space above the disc, and then the water pressure itself keeps it down. When the current is passed, the piston uncovers the centre hole and lets some water leak out. This lowers the pressure above the disc and lets it pop up and the water flow through. Today, solenoid valves have millions of uses controlling liquids and gases. For instance, the ironing machine in the laundry uses solenoid valves to release blasts of compressed air to blow the sheets flat. Each sheet hits a switch which opens the valves at precisely the right moment.
A more spectacular use for a solenoid valve is to roll a car for a stunt for film or television. We got the solenoid valve fitted on top of this tube, which is in effect a cannon, and inside the tube is a large chunk of wood which pushes the car over. In the boot of the car we've got a compressed air cylinder full of air at quite high pressure, about 150 pounds per square inch, and when I press the button, which is attached to the handbrake lever, that releases all the air through the solenoid valve, push against the wood, and whoosh, away we go. It's far better fun than a washing machine solenoid. A stunt like this is carefully planned so as hardly anything ever goes wrong. And of course, I'm tied into that seat. It's sort of painfully tight with special sort of aircraft type seat belts. It's so tight it actually hurts me, but you can't afford to move an inch or so because the impact when you roll over really does hurt. But as soon as the car starts to roll, all electric is cut so it avoids any fire. There's only a pint of petrol on board, so that if the thing did catch fire, it's a very minor fire. This is the actual cannon piston, which does the damage, which pushes it over. As you can see, it's really crude, just a piece of car inner tube to seal it on the walls of the cylinder, so when the air comes through it pushes it out. It doesn't need a lot of energy to tip it because it's almost on the point of turning before you hit the button. That's the last one I ever do. I promised that to everybody. This is the second time I've promised not to do it again. Until the next job comes along.
In this cutaway machine you can see the position of all the parts we've been looking at. There's the lump of concrete, there are the solenoid valves where the water comes in through the soap dispenser and into the drum. And this is the pressure switch.
Water is gushing into the machine through the solenoid valve, and when it reaches the right level it's got to stop, and that's what the pressure switch is for. I can show it more clearly using this bottle to replace the washing drum. So we turn the water on, and we've added some dye in here to make it a bit more clear what's happening. And the switch has switched the water off. Well, now what's actually going on is that air is trapped inside this little bottle on the side, and as the level rises the air is being squashed and actually increasing the pressure down this little pipe into the switch. I think I can show this, prove this quite clearly by, it has exactly the same effect if I blow into the switch as the little bottle on the side. So if I release the pressure, the water will start coming out, and when I blow into it, let's turn it off now. Well, what's going on inside this switch is this is one we've a similar slightly different make, but it's the same sort of thing. We've taken it in half. Now, in this half, the air goes in here, and there's a rubber disc here. And as the pressure increases, the rubber expands. On this half,
The rubber pushes the metal and flicks over the switch.
well, pressure switches, like solenoid valves, have all sorts of uses. I used one on this machine, which I made years and years ago. Put the Well, the pressure switch is used on this machine to switch the motor off when the balloon bursts. Inside here, there's a small secondary tube that goes down to the pressure switch at the back. And as long as there's the pressure inside the balloon, the motor will keep running. But when the balloon bursts, the pressure drops and that turns the motor off. Once the washing machine's full of water, the heater comes on to get it to the right temperature. You never see the heater elements because they're outside the inner drum, but they're just like the elements inside an electric kettle. We cut one in half here, and in the middle there's a fine wire, and it's this wire that actually carries the current. And closely packed all round it, there's this white powder, magnesium oxide. This is an electrical insulator to stop the outer casing becoming live. This white powder is obviously the same as the powder you get when you burn a bit of magnesium.
It's used because it retains its stability and insulation at the high temperatures inside the element.
At the same time as the water starts heating up, the wash action starts.
The speed that the drum goes round is critical. The clothes just have to get round to the top and then fall, and that's what squashes the water through them. After going one way round, they pause and then go back round the other way. This stops the clothes getting tangled up, just like in the eddy. Once the wash has finished, the next stage is the spin. But this apparently simple idea is quite recent, and early machines used much more elaborate ways to dry the clothes.
I must get this done quickly.
The mangle which squeezed the clothes dry had considerable disadvantages.
This new machine looks a lot better.
The collapsible rubber drum was even less successful.
Let's see. Oh no, it's still wet. Oh.
The principle of the spin dryer is that water is forced outwards, just like you're forced outwards on the fairground ride, the rotor. Well, in this model here, we've taken the outer casing of a spin dryer so you can see what actually goes on. In this sort, the water comes out of these slits in the middle. Well, if I get out of the way, I'll switch it on.
This is actually part of a separate spin dryer, but the automatic uses the same principle. The water is flung into an outer drum. From there, it's then pumped out the bottom.
The pump usually has a separate small motor beneath the drum, which is connected up here. Inside the pump, the water comes in through the middle, and the impeller whizzes round and round and forces the water outwards up through the waste hose. The ingenious thing about these pumps is that they resist blocking themselves up with fluff and other small objects. It does this because the impeller is much smaller than the space around it. I think we can show you how it tries not to block itself up with this model. If you start the pump going and tip some buttons into the drum, they all go straight through the pump. The central part of any automatic is the programmer timer, which switches everything on and off at the right moment.
These devices had an unlikely origin. The first automatic was made by an American company called Seeburg, who mostly made jukeboxes. In some respects, the automatic washing machine does have more in common with a jukebox than with a primitive electric washer. Both the automatic and the jukebox have timers switching a sequence of operations. Seeburg's washing machine was a failure, but it carried on making programmer timers for other companies. The modern washing machine timer is totally enclosed.
It's a lot easier to see how it works with an industrial equivalent where everything is much more spaced out. This is a small switch called a micro switch, and there are a whole row of them along the back here.
And at the end here there's a geared motor. As the motor rotates, it turns this drum round with these cams on, and these switch the micro switches on and off. Each switch is connected to a different function of the machine. Of course, on a washing machine it goes round much slower, one revolution for the complete wash cycle. I quite often use these timers because a lot of the machines I make have a sequence of actions. This one's called the chiropodist. She looks down at your foot for a bit and then looks up and twiddles her thumbs. Then she disappears beneath her counter and tickles your foot. In the past few years, microprocessors have started to replace electromechanical timers. It hasn't been easy to make a microprocessor work reliably inside the hot and steamy environment of a washing machine, and it's only quite recently, after years of development, that they've become a practical alternative.
The principle of the modern automatic has changed very little in the last 25 years, except the main difference is the price, which, adjusted for inflation, is less than half what it was.
Yeah, what seems to be the trouble, sir?
The water's got dirty washing everywhere on it.
But to make this reduction in price possible, the machines have changed a lot inside, and they're no longer built to last forever. The modern engineering would probably horrify pre-war engineers who worship quality, not economy.
Oh, look at that engineering. Oh, my God. Oh!
Oh, dear. Oh. Oh, dear. Oh.
Most of these changes have gone unnoticed. The old automatics, like the Keymatic, had complete separate chassis inside. In the modern machines, all the bits are just bolted to the outer casing. The old machines had cast iron weights, whereas the modern machines have their lumps of concrete. In the old machines, the heater wires were about twice as thick as they are now. And the pulleys, which used to be solid lumps of cast iron, are now often just really tin cans full of concrete. It's tempting to think that washing machines don't last so long as they used to, simply because they're less well made. There's some truth in this, but it's also a result of the manufacturer's great success at cutting their costs. It's now much often cheaper to buy a whole new machine than it is to pay for even a simple repair. All the machines you've seen in this programme were scrap. They cost us about £2 each, and they came from household waste tips. I hate today's disposable way of making things in all sorts of ways, but I can't help admire the ingenuity of the modern washing machine. I hope I've managed to convey some of my enthusiasm for these ingenious contraptions.